Hey everyone, in this video I'm going to show you why Karnaugh maps or K-maps are much faster and cleaner than Boolean algebra. We're going to solve the same problem twice. First we're going to use Boolean algebra and then we're going to use a K-map. And you'll understand why K-maps are much more efficient, especially during exams or tests. We're going to cover product of sums versus sum of products in a K-map, how that affects the grouping if it's ones or if the grouping is zeros, and how we use don't care conditions to dramatically simplify a logic function. So let's start with an example that we're going to solve using Boolean algebra. Say we have a function f that's given by three variables that is equivalent to these four terms over here. A naught bc plus abc plus a b naught c plus a b naught c naught. Now the way to simplify this would be first to factor out the common terms. So immediately here I see that this bc is common over there, and a b naught and a b naught is common over there. So let's go ahead and factor those out. bc a naught plus a, that's common over here and here, and then a b naught, we can factor that out to get c plus c naught over here and over here. Now using our identities, we know that a naught plus a is equal to 1 and c naught plus c is also equal to 1. Therefore, this whole equation simplifies down to bc plus a b naught. Now, this method works, but it takes multiple steps and it's easy to make mistakes, especially when your logic function might be longer, more complicated, or have several terms, not just three. So to make this simpler, we can use a K-map. K-map. The first step to solving a K-map would be to identify the minterms. So the minterms are logic ones in the map. What logic ones mean is that anything that yields your function a 1, whether that may be shown in your truth table or your expression itself, that whole term would correspond to a binary value, and that binary value can be converted into a decimal value, which corresponds to where in your K-map you will see a logic 1. So we can do that using our example over here. We see that there are four terms, a naught bc plus abc plus a b naught c plus a b naught c naught. There are four terms, and each of these terms corresponds to a logic 1 for each minterm. So if we take the first one, a naught bc, we know this corresponds to three binary digits because there's three variables correspond to 0, 1, 1. We put a 0 for a naught because it's knotted, and b and c both get a logic of 1 because they are true values. We can do that for each term in our expression. So then we have a, b, c, which corresponds to 1, 1, 1. Then you have a, b naught c. This would correspond to 1, 0, 1. Lastly, we have a, b naught, c naught. This would correspond to 1, 0, 0. So the next step would be to identifying the decimal values that each of these three binary digit values hold. So to do that, we can just convert from binary into decimal. So 0, 1, 1 would correspond to 3. So this would be minterm 3. 1, 1, 1 would correspond to 7. So this would be minterm 7. 1, 0, 1 corresponds to 5. So that would be minterm 5. And finally, 1, 0, 0 will correspond to minterm 4. Using these minterms, we're going to plot ones in our three variable K-map. Once again, three variables because function f is made up of three variables, which we can clearly see in the first logic expression. So now we're going to plot it. So we're going to put one variable on one side and the other two at the top. Just like that. Now we're going to look at the possible states to draw on the outside of the K-map that each variable can hold. So one variable can only hold two possible states, which are 0 and 1. B and C is two variables, so all the possible states that it can hold would be 0, 0, 0, 1, 1, 1, and 1, 0. Now this is the correct order of placing each possible combination of what B and C can be. The idea is each one of the binary values in B and C is only changed one time. So over here, B is not changed between these two, but C has. Only one thing has changed. And then over here, C is not changed, but B has changed. That's how you know to draw your K-map. That's the correct method. Or you can just memorize this. This is common for a 3-variable K-map or two variable K-map or 4-variable K-map. So then we can start plotting our midterms. So midterms also correspond to the binary value as we saw before. So we know that 0, 0, 0 would be midterm 0, 0, 0, 1 would be midterm 1, 0, 1, 1 would correspond to midterm 3, because converting 0, 1, 1 into decimal gives us 3, and then 0, 1, 0 would be midterm 2. And we can do the whole variable came up like that, so that would be midterm 4, midterm 5, midterm 6, and midterm 7. And then we can just simplify by drawing some lines, just like that, and like that, we will. And now we know, now our K-map is made for 3 variables, 1, 2, and 3. Now we know what our logic ones also are. They correspond to M3, M7, M5, and M4. We found that by identifying the terms in our logic expression. So let's go ahead and put logic ones in those area. So M3, M4, M5, and M7 as well. Now we've put our logic ones, we can assume that there will be logic zeros everywhere else. So 0, 0, 0, 0. Now, to simplify this K-map, we're going to first start grouping our ones. So step 1, group ones. Now there's one very important rule here. You must group in powers of 2. So 2 to the power 0, 2 to the power 1, 2 to the power 2, and so forth. Meaning, you cannot group 5 ones together because 5 is not a power of 2. So, and the easiest way to group is by first grouping the largest group of ones that you can group that correspond to a power of 2. So over here, we see that there's 3 ones on this row, but 3 does not correlate to a power of 2. But we can group these together, these ones over here. So we can write F is equal to, let's start by this grouping over here, like that in yellow. We're going to look at first the A variable. Now we know that the A variable is 1, is what we care about in this row over here. And we know that between this box over here in the K-map and the next one, A is not changing. A is remaining 1. So first we can write A because it's not changing. Now between B and C, between these two squares, we know that 0 is also, B is not also changing. If this is B and this is C, B is 0 here and B is also 0 there. But C is 0 here and C is 1 over there. So C is changing, so we can ignore it. We can put a B here. However, since when we took a look at A, we knew A was 1. We were able to just write A down since it was not changing. Now for B, we know B is not changing between these two ones, but it's a 0, so therefore we must put a naught. We can also write that as B naught. Now that we've grouped one power of 2 of ones, we can write an OR sign because we're going to do a sum of products. We're grouping ones. Now we want to group our remaining ones, which are these two over here. And we can look at first A, and once again, we're grouping these two together. You can group up, down, or left to right, it doesn't matter. Or around even, you could even go around a K-map like that, if there were ones. However, we know that 2 to the power of 1 is 2, so we can group these two together. And first, we're going to look at A. Now notice between this square and this square, A is changing. A is going from 0 and A is going to 1. So we can't write A as a term, it's changing. However, between these two, B and C is not changing. They're remaining 1. Both of them are remaining 1. Nothing else is changing. We've covered all variables, so we know that the next logic expression term would be B and C. And this is equivalent to what we found over here. BC plus AB naught plus BC. They're both the same. Now, however, this may seem longer or more counterintuitive, it indeed is much faster, especially when you're dealing with 4 variables or even a 5 variable K-map, which we'll cover later on. Moving forward, we can consider another K-map. This time, it's going to be a 4 variable K-map. It's made out of the variables A, B, C, and D, and is given by the notation sigma m, which essentially means the sum of minterms 0, 2, 8, and 10. As we previously saw, these values of minterms are logic 1s in our K-map. So we can essentially say that minterms 0, 2, 8, and 10 would correlate to what value in binary in our K-map, since we know there are logic 1s here. Minterm 0 would be 0, 0, 0, 0. Minterm 2 would be 0, 0, 1, 0. Minterm 8 would be 1, 0, 0, 0. And minterm 10 would be 1, 0, 1, 0. The reason why we use 4 binary values is because there are 4 variables to consider in this K-map. So now that we know there will be logic 1s in each of these places in our K-map, we can go ahead and draw it. The first step would be to draw the outsides of the K-map. So to draw a 4 variable K-map, we know that we can have 2 variables on one side and the other 2 on the other. So we can put A and B over here and C and D over here. And then we can simply draw the outsides. And just like before, we want to consider all the possible scenarios that each of those variables can take on for the outside of the K-map. So what can A and B? What are all the possible scenarios that A and B can possibly be? Well, A and B can be 0, 0. It can be 0, 1, 1, 1, and 1, 0. Same with C and D. It can be 0, 0, 0, 1, 1, 1, and 1, 0. The reason why we go in this manner would be, well, just like before, we want to make sure between A and B and the next state, only one variable is changing at a time. Over here, we can see that only B is changing. And then from here to here, we can see that B is staying the same, but C is changing. So that's the idea that you can consider, or you can just memorize how to draw the outsides of these K-maps. Then we can draw our outlines like this. We can ignore that. And then we know that we want to put logic 1s in each of these areas. The first step we can do is by putting a logic 1 in minterm 0. So that's 0, 0, 0, 0. Where do you see 0, 0, 0, 0 in this K-map? Well, it would be right here. So you're going to put a logic 1 there. That's minterm 0. Then you can go ahead and do 0, 0, 1, 0, which is over here. Then you can do 1, 0, 0, 0, which is here. And 1, 0, 1, 0, which is here. So it would be minterm 2, minterm 8, and minterm 10. Now you know that there would be zeros everywhere else on this K-map. Just keep in mind, for the sake of this example, we ignore this first row just because there's no values over here. It's just the notation of A and B. So we can ignore this whole top column. Anyway, now for the grouping. As we previously saw, we want to group the ones in our K-map for sum of products as powers of 2. Well, over here, you may say that there's 4 ones, which is the power of 2. 2 to the power of 2 is 4, but we can't group them because they're not side by side to each other. Well, here's the beauty of a K-map. The idea of a K-map is you can group each of the ones around the K-map from both sides, up and down. So if we're going around the K-map, you can notice that this one is connected to this one if you had to turn the map over or roll it, if you could visualize that. And if you do that way, these two ones can be grouped together. But if you visualize yourself folding this map the other way, you would also notice that, this one and this one are also connected to these two ones over here. That's because when you can wrap around in a K-map, you can form bigger groups of ones that make the job of simplification much easier. So we can go ahead and group all these ones despite being on different edges of our K-map together. Here's an important note. Remember, in K-maps, you can group around the corners and use the wrap around method. We're grouping around the map like this to get all the ones. Imagine you can picture yourself kind of rolling this map in order to understand this grouping. Anyway, going forward, to write our final expression of f, we can evaluate all these ones and see what is changing. We can look at a first. Well, there's a 1 here and a has changed from 0 to 1, so we can ignore that. In this one and this one, and all 4 of these actually, b is staying the same, but it's a 0, so we know that we want to put b not. Now we're going to evaluate the top row, and since this is the same grouping, we're not evaluating a different group, we do not put a plus sign, because we're still evaluating the same group. For that reason, we can look at the top variable. We can see between all 4 of these ones, C has changed, so we're going to ignore that. However, D is staying the same. In the column where there's all ones, it's 0 over here, and it's 0 over there, so we know to put D not. Therefore, our final answer would be f is equal to b naught, d naught. Here's another example of a clean 4-variable product of sums K-map, where we're going to use max terms, which indicate to us that we're going to do a product of sums rather than a sum of products. It's given by the following notation: pi and capital M, which gives us the list of max terms that are K-map, that we're going to put zeros in our K-maps for. And instead of grouping ones, we're going to group zeros, however, with the same rule. In order to do that, just like before, we're going to identify each of these max terms and correspond them to a specific binary value. So it'll be max term 1, max term 3, max term 5, max term 7, max term 9, max term 11, 13, and 15. Each of these will correspond to a 4-digit binary number. The reason why it's 4 is once again because there are 4 variables in our K-map. So max term 1 corresponding to 1 would be in binary 0, 0, 0, 1. Then max term 3 would be 0, 0, 1, 1. Max term 5 would be 0, 1, 0, 1. Max term 7 would be 0, 1, 1, 1. Max term 9 would be 1, 0, 0, 1. Max term 11 would be 1, 0, 1, 1. And max term 13 would be 1, 1, 0, 1. And finally, max term 15 would be 1, 1, 1, 1. Now we know just like before, there's going to be logic zeros in the K-map. Why zeros this time? Well, because we're doing a POS, max terms, instead of minterms. So we can go ahead and draw this K-mat out. So we're going to do A and B, C and D. We're going to write 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. You can draw outlines, K-map to get the squares, just like that. And we know that logic zeros this time instead of ones, because it's max terms, would be in each of these minterms. So we're going to go ahead and put that. And if you are quick, you can realize that there's going to be zeros in each of these. And therefore, you can also put ones elsewhere. Oops, we need that there. So zeros and ones everywhere else. Now that we know that, we can group zeros together in the same manner that we grouped ones in powers of 2. But you have to be careful not to start grouping ones, because this time we're doing product of sums, which is given by the pi symbol. That's your indication that you need to do product of sums rather than sum of products. The largest group of zeros that are in powers of 2 are going to be right here. There are 8 zeros, all grouped right down in the center of our K-map. Looking at each variable, we know that A is changing from here to here to here to here. It went from 0 to 1, so we're going to ignore that. B is also changing because immediately in our grouping, we see that B goes from 0 to 1, and we're still grouping our zeros. So we're going to go ahead and look at C and D. C is also changing, so we're going to go ahead and ignore that. However, D is not changing, so we're going to keep D over here. Is equal to D. There's one thing special about this, however, is that if we write F is equal to D, then we can say that when D is equal to logic 1, then F must be 1. However, when we're looking at our K-map, D equals 1 is a logic 0. We see that in our K-map. The function is 0. Those are the max term, not the min terms. Therefore, we know that D must be the opposite of what we actually need. So F is actually equal to D prime. That's the correct answer. For the last part of this video, we're going to look at the don't cares method for analyzing K-maps. Don't cares are actually a great way for you to easily solve your K-map and can make it much easier to simplify down to the simplest form of the logic expression of that specific function. So over here, we see the notation that F is made up of 4 variables, A, B, C, D, and given by the minterms, the sum of minterms 0 to 8, 10, 11, and 15, plus this notation D1, 9. What that is referring to is our don't cares are in boxes 1 and 9. And we can mark those as an X. And just like before from the first example we saw, our minterms correspond to logic 1s in their boxes. Going ahead with our regular steps, we know that their midterm 0 to 8, 10, 11, and 15. Midterm 0 will correspond to 0, 0, 0, 0. Midterm 2, 0, 0, 1, 0. Midterm 8, 1, 0, 0, 0. Midterm 10, 1, 0, 1, 0. Midterm 11, 1, 0, 1, 1. Midterm 15, 1, 1, 1, 1. And then our don't cares So let's say this is M, this would be our D. We're going to say they're at 1 and 9. So we're going to say D1 would be at 0, 0, 0, 1, and D9 would be at 1, 0, 0, 1. Once again, it's important to note that all we're doing is taking each of these minterm values and correlating them to their binary value equivalency. So 0 in binary would be what? And that's this over here. Once again, we're using 4 binary digits because there are 4 variables in this function. Now let's go ahead and draw this out, keeping in mind that we're going to place ones in all of these minterms and x's in all of these don't cares. Now that we've drawn out our 4 variable k-map with a and b as the rows and c and d as the columns, we can go ahead and put the ones in all of these corresponding minterms. So that's going to be in minterm 0, there's going to be a 1 over here, over here, over here, over here, and over here. Now, before we go ahead and place our zeros everywhere else, we're also going to put the x as don't cares in their corresponding boxes of binary values 1 and 9. So 0, 0, 0, 1 would be here, 0, 0, 0, 1. So we know that an x is going to be placed over here. Similarly, with D9, 1, 0, 0, 1, we know an x is also going to be placed here. And now we know that we can go ahead and group and place zeros everywhere else. Now we can go ahead with our grouping. Just like before, we want to group each one as powers of 2 and as largest as we possibly can. Over here, we see that there's 1, 2, 3, 4, 5, 6 ones. However, the beauty of the don't care x's is that we can treat them at once. We don't care whether the function outputs 0 or 1 for that specific input value of a, b, and c, and d. Therefore, we can use them to our advantage and make bigger groups of ones to make the job much more simplified. These ones over here, just like before, we're using the wraparound method to wrap around the k-map and make the largest group of ones we possibly can. Over here, our first term in our expression would be the grouping of these 4 ones around the corner. So we're going to look at each variable and see what's changing across this grouping. We see here that b is always staying 0 in this. So we're going to put b. However, it's 0, so we're going to put a not. And c is changing from 0 to 1, so we can ignore that. But it's also staying 0, so we can put a d not. Now we know that we've done grouping one group of ones. We can put a plus sign because we're back to doing sum of products given by this hint, sum of minterms. Our next grouping would be these 2 ones over here. The reason why we're not yet looking at the x's right now is because we want to be the most efficient with the k-map as we possibly can. If I can already group these 4 ones together, I won't need to use the don't care x's. Of course, I can use other methods by just grouping this whole line together if I wanted to, because after all, I can treat this x as a 1, and then go ahead and group maybe these 2 together, this one, and then this one. However, that wouldn't be as efficient as grouping the largest group of ones that are possible. So we can go ahead and do that. And we can group these ones over here. Over here, we see that A is not changing, so we can put an A there. And then finally, we can look at the top. C and D is also not changing, so we can just put C and D over here and get our final simplified answer in sum of products form for this function. Just to reiterate, we actually didn't use the don't care conditions because they didn't simplify our grouping. We wanted to group the largest group first, therefore we grouped these 4 ones first rather than this whole first line, because later on, if we group this line together first, we're going to have to group these 2 next, which is leaving 2 separate group of ones that we could not group. Therefore, it's important to note that before starting your grouping, you want to see what's the largest and most efficient grouping you can possibly make.